it's 5 o'clock. Belén, should we start?
Yeah, I think if it is really 5 well marked, let's start, right?
According to my clock.
Yeah, to mine too. It's just giving 20 seconds margin on the 5, but that is because people are piling up as always at the last minute, but that's okay. Please go ahead.
Okay, so welcome back to the final session of the workshop, and our first speaker now is Juna Kroon from Triumph and Dharam, who will be telling us about gravitational waves for, I guess, fundamental physics. Thank you, Juna.
Yeah, thanks for having me. I always like talking to an Invisibles audience, although never more as Invisibles as now, because you're literally invisible to me as I present these slides to my computer screen. So yeah, I like this title, like I gave it a while ago, but when I was actually writing the slides, I decided it would be more fun to actually change the order a little bit. So I'm first going to talk about the kind of promise of this research program, the promise that gravitational waves have for early universe fundamental research. And then once I've hooked you in, hopefully I'm going to talk about the challenges and in the hope that maybe you'll help with them. So good. Whoops. So let's start off like talking about a timeline of our very early universe. And when I say very early, I really mean this, first seconds in particular, because we have questions about it. And I've collected a few of these questions here. So it relates to some of our deepest questions about fundamental physics. And these will certainly have an answer in this first second. But that being said, I am always really amazed with how much we do actually know about this first second. And a good way to sort of get a feel for how much we know about it is to try and come up with your own theory that changes something about our cosmic history of this first second, and see how easy it is to mess that up. And it's easy because we already do know so much observationally. That's quite remarkable because to date, our observational probes of the second are somewhat indirect. And the reason is that what we use as our probes are photons and neutrinos and sometimes light element abundances, as many of the speakers have talked about. But during this first second in particular, the universe would have been opaque to these particles. And so meaning that because of the thermal equilibrium, any kind of events that source some of these particles would have immediately been reabsorbed in the plasma. And so it's not something we can detect today. And so a direct cosmological probe is the CMB. That's what people sometimes call a baby picture of our universe. And we learned a lot from the CMB. But really, it's if I put this on this timeline, it's quite far after the eras we're very interested in. And so that is one of the promises of gravitational waves. Unlike photons, gravitational particles, gravitational waves would not have been in thermal equilibrium. So a source of gravitational waves in the early universe could lead to a direct detection, direct experimental information from this period. Now, there's different sources, potential sources of gravitational waves in the early universe, and I'm mostly interested in cosmological first order phase transition. So that's what the rest of this talk is going to be focused on. So what's this source like? So phase transition, as you know, it's like a transition of the phase of the universe. The vacuum state changes, and such a change is first order if it doesn't change homogeneously and smoothly and boringly, except instead it kind of has this kind of disruptive process to it. So here, if I express this in terms of some scalar order parameter and its potential energy, the phase transition means that the vacuum state changes. The first orderness of it is to do with when these vacua are degenerate, there is a kind of a barrier separating these different things. So you can't just smoothly transition into this new state. You have to fluctuate through or over the barrier. And when that happens, a bubble nucleated of this new vacuum, and because it's energetically favored to be in this new vacuum, there's this pressure outwards and these bubbles start to grow. And as they grow, that's kind of a disruptive process. So they interact with each other, they collide, but they also interact with the rest of the plasma, primordial plasma. And all of this stuff has kind of non-spherically symmetric, interesting motions, and its source is gravitational waves. So then how do we know what's the gravitational wave spectrum in such a process is? Well, we can do theoretical calculations, but we also use simulations to kind of relate it to spectra that we can observe today. So what types of things, how would that spectrum look like? What would the spectrum look like? Whoops. Now, there's a few different processes that source gravitational waves. So first, like you might have the collisions of these bubbles themselves. So this is really a kind of a scalar field profile sourcing gravitational waves. What we like to use to express such a spectrum is this omega gravitational wave parameter. It is really kind of the thing that if you integrated it, you get the total kind of energy density fraction in gravitational waves. So it's like a differential energy fraction as a function of the frequency of the spectrum. And so like you get this sort of collision type term. You also get contributions from just the plasma oscillations that kind of keep going on after the phase transition. So like these bubbles source like kind of motion in the plasma, and that keeps sourcing gravitational waves potentially for a long time afterwards. So these three different contributions scale slightly differently. So what you see here is like, here, there's kind of this feature in all of these different frequencies, and this is kind of because this process has a horizon, if you will, and this horizon really kind of changes how the spectrum looks. And it means that there's a peak, and that peak is kind of roughly related to the size of the bubble at collision, or the size of the sound shells at collision. And so you see that, before that type of break, all of these different contributions scale in the same way. This is just kind of given by causality, but then afterwards they scale differently. Because this is kind of like, because you have a spectrum with a peak, that also kind of helps maybe distinguish from other types of signals from the early universe or from the late universe, just because they scale very differently with frequency. So hopefully that's a way to distinguish. Okay, the other thing, because it has a peak, you can actually kind of draw a kind of intuitive picture of what type of era in our cosmic history you're sensitive to with what type of spectrum. And so the first thing that I've done here is like I've related this time in seconds since the Big Bang, or since the beginning of time, if you will. I've related that to a temperature of the universe, like the radiation bath of the early universe. So just assuming radiation domination, assuming like a particular number of degrees of freedom, you can draw this type of comparison. And then from this temperature, you can then also relate with some assumptions that I've made that are relatively minimal to a characteristic frequency of a gravitational wave spectrum. And so this kind of picture can give you some intuition for what type of experiment can help you probe what type of cosmological era. And in particular, ground-based interferometers, such the ones that are operational now, like LIGO and Virgo, but also future generations, such as like the Einstein telescope, they are sensitive to this early time, so actually very high temperatures. And space-based interferometers such as LISA, which are under construction now, give you access to this kind of interesting era, including the weak scale. Then indirect observations would probe like even later times. This is kind of a difficult thing to disentangle. Of course, you don't want to mess with BBN too much. Atom interferometry, I wanted to give a shout out. Like that's kind of a field that's been like really developing pretty rapidly in the last few years, and that would kind of potentially probe actually this gap between space and ground-based interferometers. Okay, now then, as Shada already said in the talk before me, the standard model doesn't have a first order phase transition in the early universe, and so any type of signal like this gives you a direct hint of new physics. Now, okay, why would you expect a first order phase transition in a model of new physics? Well, there are various reasons. One kind of very popular and good reason is that some models of baryogenesis, such as what Shada talked about this morning, although she talked about a different type of setup, baryogenesis, like to generate a baryonyl asymmetry, you need to satisfy these Sakharov conditions, which you're probably very familiar with. One of these conditions is like out of equilibrium reactions. And so that's just, making sure that baryogenesis is irreversible. But in many models, first order phase transitions play that role. Then there's been many models in which a dark sector, so, dark sector also needs to have a mass mechanism, also needs to have, satisfy particular things. And so a dark sector, could have also a first order phase transition. We know that the standard model, like electric symmetry breaking, is in the standard model, it's not a first order phase transition, but there's no reason to expect that a similar type of mass mechanism in a dark sector has any type of order of a phase transition. So there's been also many papers like exploring this. One thing to remark is that for the gravitational wave spectrum to be observable, it means that actually a very large fraction of the energy in the universe at the time of transition would have participated. So it gives you something that's not negligible. So dark sector might be something like that. Then particular models of confinement, again, typically with a chiral symmetry which is larger than the standard model at the time of confinement. And so, for example, models where you have a large number of massless flavors, could also lead to a first order phase transition. And then, models in which you have a grand unified theory, but you don't have SUSY, that typically gives rise to this cascade of different intermediate, symmetry breaking scales, each of which would lead to a phase transition, which could be first order. So that's also been explored. So, there's many different, there's kind of many different models in which this plays an important role. And I think the thing to remember is that it is kind of a hint of something beyond the standard model, because nothing like this happens in the standard model. So if we would see such a characteristic spectrum, that's a good indication that something is different than what we expected. Okay, so now I've talked a bit about some of these opportunities. I want to skip, I want to go to the challenges that are remaining, before we can actually make reliable predictions and actually do phenomenology with this type of thing. And so, I've given you kind of this explanation of how a phase transition, a first order phase transition works. And I'm going to separate it back into these three different components to talk about the challenges. Now, I mostly work on this first part. So actually, going from a particular microphysics model to this, the kind of thermal parameters of the phase transition, if you will. And what's most important here is calculating the decay rates of the false vacuum. So basically doing this kind of tunneling calculation, first calculating this effective potential, and then calculating this tunnel rates. And it gives you kind of, information of how these bubbles actually nucleate. Now, so you would think this is, you would potentially think that this is the step that's most under control, because it's just kind of a, something that we know how to work with very well, like a microphysics calculation, but there's some challenges with it, and let me sort of allude to that. So some of the problems relate to actually our kind of grasp of perturbativity and thermal field theory exactly around scales of the phase transition. And so I, with a few collaborators last year, we wrote this paper, kind of exploring systematically all of the different sources of theoretical uncertainty in this prediction. So we have a benchmark model. This is kind of a benchmark model that can stand in for different types of electroweak symmetry breaking models. So where you have the standard model plus this dimension 6 operator, and the electroweak symmetry is broken in a way that gives rise to a first order phase transition. And so what we calculated is all of these different sources of variation of a theoretical input parameter, variation of the spectrum with respect to a theoretical input parameter, such as, for example, the renormalization scale that you choose. And so that's kind of variation with a parameter that you don't want to be sensitive to, if you will. This is kind of the summary plot of that paper. I won't have time to go into the whole paper in too much detail, but what you see here in particular, which kind of worries some, is that this here is the relative uncertainty in the spectrum. And so if this is much above 1, which it is in the 4D calculation people do often, then you really don't have an idea, like, you know, where it is, like how big this spectrum is. Then that's of course still in a perturbative theory. If you go to a strongly coupled theory, then really all bets are off. Well, we have of course very good models for the low energy and then also for the high energy phases of strongly coupled theories, but actually, you know, studying theoretically like the phase transition is a real challenge here. And so some of the models that have been used, you know, they lead to inconsistent results as well. Okay, so let's go back to you know, why it is that this is such a difficult calculation, since, you know, you would think maybe that that's the stuff that's mostly under control. So, you know, the method that people use typically to calculate the false vacuum decay rates is like the bounce method, which is, you know, quite an old method, and essentially it works as a saddle point approximation. So the thing I want to know about is this like imaginary part of the Euclidean energy, and that gives me the false vacuum decay rates. And so how I get to that is essentially like a saddle point approximation. So first, what you know write down is this path integral, and what you can notice is that, you know, for such a solution, the path integral can be dominated by the solutions to the Euclidean equations of motion. And so I can really just expand around those. And if I do that, of course, because these are solutions to the Euclidean equation of motion, the linear term should vanish. And what I end up with is, you know, this type of setup where I can then again, like just factor out, you know, this term. And all I really have to do then in the end is like do this Gaussian integral over this you know, fluctuation and find the Euclidean the solution to the Euclidean equations of motion, and that is then the bounce. Now that's a very interesting, like, and good mechanism. However, an issue with it is that you have to assume that there exists a solution to the Euclidean equation of motion that's a bounce solution at tree level. And sometimes a phase transition is actually not generated at tree level, but it is like rather a you know, something that is only generated at the radiative level. And so how to sort of then adapt this type of mechanism is not so easy. So one thing that people do is coarse graining. So what you do in that case is like actually separating out in the effective action high energy and low energy momentum modes, and you find the bounds for these low energy modes. So like essentially you're doing a derivative expansion where you're separating like the UV and the IR. And so variations of this type of tool exist. So in our paper, we looked, for example, at a 3D setup, which essentially works in this way. And so that's better than you know, just doing the naive thing. But it still does have a downside because you still have some dependence on the renormalization scale, and also most importantly on like perturbativity of the model. Then what I like to, you know, something I like to sort of mention is like a program that I've been working on most recently with Hitoshi, who spoke yesterday, and Eleanor Hall, who is a really great graduate student at Berkeley. And we have actually kind of a new thing that we're thinking about to improve this calculation. And that is like through the assumption that like, you know, the bounce action is dominated by, not by these solutions to the Euclidean equation of motion, but actually patches, you know, that dominate the path integral. And if we assume that it doesn't really matter like what the, you know, shape of these patches are, as long as we encompass, like as long as they enclose these solutions. And so you can, you know, you might as well choose something simple. And you know, all we really kind of want to enforce is that, you know, you are sort of choosing sort of like locality in field space by kind of assuming that like the integral is dominated by bounce-like patches. But then you might ask, okay, how, I know how to, separate high energy and low energy modes, but how do I impose something like that? So to do that, like what we use is like this non-perturbative formalism, you like call the functional renormalization. So really what you're doing is like you are finding the flow of the effective action, as a function like of its like the action and its regulator. So basically what this does, it's like it's a differential equation for the effective action as a function of scale. Let me just give you a very brief, 5 minutes, I know, a very brief, like quick picture of how this works. So you start off with like the effective action that you know and love, but you add a term which takes care of like regulating the fluctuations in such a way that you consecutively take into account fluctuations of different size. So you start at like an input scale and you just flow back to the IR. And as you're lowering this K, this scale, you ensure that like fluctuations are taken into account successively. And you end up with like the final action at K equals 0. So, the proposal now is like to make this regulator term do some more work by actually also imposing locality. And that's been like an interesting thing to explore. I'll just give you some brief like overview. You see that here on the left-hand side, I'm showing you the results in a regime that you would expect perturbation theory to work. And you see you get the exact same results. But here in this regime where you have stronger coupling, it gives you a different result. Okay, so that's something we're working on. Currently, we're actually looking at like how that actually impacts the decay rates. But let me just in the final minutes, like talk a little bit about the rest of these things that I, don't personally work on so much, but also have interesting questions. So in particular, this step of bubble expansion, what you really want to know is like, these forces on the bubble wall, how do they balance, or do they balance at any point? And the reason it's important is because you want to know how much energy of this phase transition is going into the plasma versus how much stays in the scalar field in the bubble wall. So there's been a lot of like there's been a lot of progression in this and understanding of this recently. So in 2009, there was a calculation which actually would show, like in a simple calculation, that these bubbles can run away, meaning they can keep expanding and never actually hit the pressure on the bubble wall, which like such that it reaches a terminal velocity. But then very recently, actually, it's been shown that that's actually not like the case, because if you consider also the transition radiation that would originate from this bubble wall in the phase transition, you do actually have an increasing thermal pressure with the velocity of the bubble wall. And so you actually, at some point, it acts as a brake, and at some point, these things are in balance. And even more recently, if you do this like calculation in full generality, and so you allow for n particles of like transition radiation, it's even like you find even a stronger kind of break, if you will. And so the reason that's important is because it tells you something about like how much energy is going into the plasma. Okay, and the very last thing is even if you're assuming that like all of the that the thermal, the sort of primordial plasma has a lot of this motion after the phase transition, how that actually scales, how the spectrum actually scales with that motion. And so especially because like, acoustic waves in the plasma, these are these kind of nice sound shells, which source gravitational radiation potentially for a very long time. Once you've done a simulation, you need to actually scale to cosmic time to figure out, how big the spectrum actually is. But acoustic waves don't stay in the plasma forever and keep sourcing gravitational waves. Eventually, they decay into like a turbulent plasma, and when that happens, energy is like kind of going into sort of smaller and smaller scales, and eventually, like all of this is dissipated. And of course, these things no longer source gravitational radiation. And so the real question then is, okay, so the spectrum will, the spectrum of the acoustic waves, which source gravitational waves, depends on the time scale that these acoustic waves are around in the plasma. And, eventually they decay, but what's really important is this time at which they do. And that's a big question. And it's hard to do this in simulations because, to resolve all of these different scales in one simulation is a challenge. And so, the time scale for this to happen is a big question. There are estimates, but as you can see, the spectrum really directly scales with that. So it's an important thing to figure out as well. Okay, so I've given you a flavor of this research program. First, I started sort of trying to convince you of like, how interesting it is and what the promise is of this research program. First order phase transitions in the early universe would be, like potentially our first direct, would lead to our first direct observational probe and of these first seconds, and also immediately imply beyond the standard model of physics. But accurate predictions is like a challenging thing, and there's different ways in which it is challenging. So even like in the microphysics sense, at the onset, the nucleation rate of bubbles is a challenge. Then I talked a little bit about like, how these bubbles then expand, which is important for how much energy goes into the plasma. And then even, when you start off after the phase transition and you study the plasma dynamics, there's remaining questions about like how long you have this nice linear acoustic motion in the plasma and how quickly that decays into turbulence. So thanks a lot. And yeah, ask me anything you like or just email me, if you have a question.
Thank you very much, Juna. Other questions? So there is Jörg, Jackal. You can.
Yeah. I actually have a bit of a technical question. In this effective action approach, to what degree does what you differ from the approach of just taking the scale-dependent effective action and evaluating it at the scale of the size of the bubble and basically determining this self-consistently?
Oh yeah, good question. Yeah, I wish I had already made a plot about this. Yeah, so I think what you're saying is like you're studying the flow of this effective action. There's the scale here. What I can do is also choose a characteristic scale, which maybe relates to like the size of the bubble or etc. and evaluate it here. So that is actually kind of very similar to this kind of coarse graining, right? So if like, so
that's in a sense a standard strategy for the coarse-grained effective action, I would think.
Yeah. So I mean, I don't have like references to that here, but in that method, like, so this type of like coarse graining, also if you do it like in the FRG way, you still like have kind of some you still rely on like perturbativity, and so there's like some papers, for example, by Wetterich and Tetradis, where you show that kind of counterintuitively, like, but you still kind of have this dependence on like I think it's like the coupling times k, if you will. Whereas the hope is that like because like doing it in this way, like you get you don't have any kind of like reliance on perturbativity. So I mean, we are kind of actually using a different regulator which has which cuts off like fluctuation sizes, and we go all the way to 0, and numerically also like it gives you a different result. But maybe I can sort of like it's a kind of a big question for like but
thanks.
Any other question? Please just raise your hand. You have the symbol in reactions or in the participants. Okay, I don't see any further question. So I'm curious. I mean, aren't these calculations something you can also do on the lattice?
Yeah.
People try to study the phase transition in the standard model. In the end, it was the lattice method that answered this for good. So I wonder if, there
Yeah,
are.
definitely. Yeah, especially in this like in the regime where like you don't actually have that much like theoretical control, especially like for these strongly coupled theories. Yes, you could. Yeah. So most sort of lattice attention has been paid to the standard model, like which is makes sense. But yeah, like you could also study this on the lattice, and in particular determine the order of the phase transition, and I think like the like gap, like the energetic sort of gap scales. So yeah, like ultimately, like it'd be good to compare this type of theoretical calculation to what you could do on the lattice in models of like chiral symmetry breaking. Yeah.
Okay, thank you. Any other question or comment for you now? Okay, I don't see anything else. So again, as usual, you can look for questions in Slack. So thank you very much, Yuna, for this nice talk. And now we pass to the last lecture, talk of the session today. And it is an honor and privilege to introduce Professor Andrea Goetz from the University of California at Los Angeles, who, as you know, is also last year's winner of the Nobel Prize in Physics for the discovery of a supermassive compact object in the Milky Way. A prize she shared with Reinhard Getzel and Roger Penrose. So Professor Goetz has been the fourth female physicist to be awarded the Nobel Prize, as you know. And in our much shorter history of Invisibles meetings, she's also the fourth Nobel laureate to participate in our meetings, for which we are most grateful. So I just pass the microphone to Professor Goetz.
Thank you. It's a pleasure to be here. Let me just get my slides shared here, and hopefully, can you see them?
Yes.
Okay, great. So I'm thrilled to be able to share the work that we've been doing over the last 26 years at the center of the galaxy, originally driven by the question, is there a supermassive black hole at the center of the galaxy, as a way of demonstrating that these objects exist. Before I get too far into this, I really want to give a lot of credit to my collaborators. This is a program that started off with a very small team. And I really, in particular, want to note Eric Becklin and Mark Morris, who I've collaborated with through this entire time. And then my very first grad student, Beth Klein. Since then, this project, the scope has expanded scientifically, in large part because the technology has advanced so much. But along with that expansion has come with an expansion of the team. So today, the core team is about 30 people. And in particular, I'd like to call out Tuan Do and Jessica Liu, who both started as graduate students on this project and now are professors with their own students and postdocs collaborating on this project. This project has also now become a key science case for the development of high resolution imaging technology at the Keck telescope, as well as for the future 30-meter telescope. And in that endeavor, we have a broader network of about 100 people that we work with. So this is it's been a fascinating journey of going from a project. Actually, that I'll share that the first I came to UCLA to get access to the Keck Observatory, and my very first proposal to do this project was actually turned down. So it's gone from something where we are having to fight to get on the telescope and a very small team to a very different enterprise. So it's been a really interesting and lots of delightful journey of the development of science. So there's two very big picture perspectives on the science behind this project. From a physics perspective, the original question was driven by the question of, do supermassive black holes exist? And then today, that's moved into the question of understanding how gravity works near, in the vicinity of a supermassive black hole. So really trying to get at tests of Einstein's theory of general relativity in regimes that have not been explored before. So while these objects are outcomes of his ideas, we also know that they also represent the breakdown of our understanding of how general relativity works with quantum mechanics. A second big picture perspective is looking at the astrophysical role that these objects play in the formation and evolution of galaxies. So while at the outset of this project, when we were first reporting the results, the thinking around the relationship between supermassive black holes, the ones that are 1 million to 1 billion times the mass of the sun, and the host galaxies, was a framing of which came first, the black hole or the galaxy, very much like the chicken or the egg question, which came first. But today we understand that is probably not the correct framework, because today we recognize that there's a correlation between the mass of supermassive black holes and the mass of their host galaxies, and in particular, the bulge of these galaxies. It's a very well-defined relationship where the mass seems to be roughly 0.1% of the mass of the central part of the galaxy. So in looking at this, we have a unique opportunity to look at the feedback that must exist between the central black hole and their host galaxy. All right, to really go back and look at what we're trying to do, the most direct test of the existence of black holes is to demonstrate that there is some amount of mass confined within its short shield radius. So remembering that the short shield radius is just an abstract size, because the black hole itself has no finite size. And if we think about the case for these different kinds of black holes, I just want to remind us that the idea of black holes was generated by our thinking about stellar mass black holes that are roughly 10 times the mass of the sun. And these things were originally thought of when people were considering the evolution of the most massive stars in our galaxy. So stars that were more massive than 30 times the mass of the sun. It was theoretically predicted that these would become black holes. So theory led, and observations have beautifully supported the existence of stellar mass black holes. In particular, the gravitational wave experiments really demonstrate the existence of these objects. The case for the supermassive black holes is quite different. These were not predicted theoretically, but rather it was observations that suggested the existence of these objects. In particular, observations of galaxies known as active galactic nuclei, or AGN for short. And in these galaxies, as their name suggests, their nuclei or centers are very active. This is a picture taken at radio wavelengths, so very long wavelength observations, that highlights two phenomena in particular that drove the thinking about supermassive black holes. The first is the presence of these really energetic jets of emission that are coming out from the core. So you can measure the kinematic energy of these jets, and that suggests a very powerful central engine. The second piece of evidence that people pointed to was the emission at the core, really at the center of the galaxy, where the emission was unlike anything produced by stars or gas in the rest of the galaxy. And the gas, this emission suggested very high velocities, so suggesting a very compact object. So it was these observations that suggested roughly half a century ago that it was possible to think about black holes that would be 1 million to 1 billion times the mass of the sun. So this is what motivated the thinking about supermassive black holes. And very quickly, this led to the idea that maybe all galaxies harbor supermassive black holes, and not just this subset of AGNs, which are roughly 10% of all galaxies. Now, so we're going to look for supermassive black holes at the center of normal galaxies, and there's nothing in particular that suggests the presence of a black hole at the center. And I just want to highlight that if this is a galaxy that would look very much like our own if we could get outside of it and look back. Of course, our sun is about halfway out and we're looking towards the center. And the center of galaxies, even in normal galaxies, are much more extreme than out here in what I would call the stellar the suburbs of the galaxy. The densities are much higher. They're about a billion times higher. And almost any way you can describe the properties of the galaxy, they get much more extreme at the center of the galaxy. And this is going to come back later in the talk, where we look at the astrophysical richness of this environment around the central supermassive black hole. Now, our galaxy is certainly the best place to look for the presence of a supermassive black hole at the center of galaxies, because it has the advantage of being the closest center of a galaxy that we'll ever have to study. The next closest galaxy is 100 times further away. So we have a lot more ability to see a lot more detail. So that's definitely the advantage of studying the center of the galaxy. But like in life, for every pro, there's usually a con. And the con comes from the fact that we live in the galaxy and that we have to look through the plane of the galaxy towards the center to see it. So this is a picture, a photograph actually from from Hawaii, the side of on the Big Island on Mauna Kea, which is actually where the telescope that we use is located. And what you see very beautifully is the plane of the galaxy through the starlight, but you presumably will also notice the dust lane that travels through the center of the galaxy or through the plane of the galaxy. So our galaxy has a tremendous amount of dust in addition to all the stars that reside in our galaxy. And that dust is very good at obstructing optical light. So only 1 out of every 10 billion photons that are emitted from the center of the galaxy makes it to us. So it's basically invisible at optical wavelengths. But if you go to the infrared, and in particular 2 microns, 1 out of every 10 photons makes it to us so that we can actually detect it. So a key part of this experiment, there's many technical developments that led to this experiment becoming possible, but one of the first ones was the advances in infrared detectors, and in particular low read noise detectors that were really being developed or making lots of progress roughly 30 years ago when we began this project. All right, so this is an overly simplistic picture of what we're trying to do, but lets us think about the observations. So the key here is to make a dynamical measurement of the mass at the center of the galaxy. And there are many approaches to getting dynamical masses. In the beginning, when we first proposed this experiment, we proposed it as a project to go for just 3 years. And even that at the time was, people were skeptical that it would work for reasons that I'll get into in a minute. So the idea was to measure the velocity dispersion, which is a pretty standard technique for measuring the dynamical mass of a system. So we were looking at the ensemble average or the dispersion of the velocities. And the way this was not traditional is typically people look at spectra to measure the velocity dispersion along your line of sight. But what we were proposing here was actually to take images, a sequence of images, and to measure the proper motions. So to get the proper motions individually and to get the plane of the sky dispersion. Okay, if that ended up working out incredibly well. And for reasons, well, actually, it's sort of interesting in terms of the tension that this created, because in the early days, there was a lot of skepticism about whether or not what we were seeing was actually a black hole. And these ensemble average techniques have a lot of embedded assumptions, so that you assume the distribution of stars, you assume the kinds of orbits they're on to get the masses. Furthermore, because you're taking an average, you're measuring an enclosed mass that's within a statistical average. So to do better, you can go to the individual orbits. So once we had actually gotten to this point, it became clear that the individual orbits were possible. And that's what really got us going on a very long-term project, which was to measure the individual orbits. That eliminates all assumptions about the kinds of orbits and the distributions of the stars that you're measuring, and allows you to confine the mass to a much smaller volume, which really advances the argument for the black hole by quite a bit. Okay, so because the goal is to detect the stars that are as close to the center of the galaxy as possible, the key to this experiment is to get to the highest angular resolution possible. So that tells you why I was interested in getting access to the Keck telescope. So I actually came to UCLA because I really wanted to use it was new at the time, to use these telescopes in a new and different way. Maybe to explain or to help people understand why the experiment, which now seems so obvious, was controversial in the beginning. One of the things that one of the technical innovations of the Keck telescope, so this is the largest telescope in the world at optical and infrared wavelengths, and the way it achieved the diameter of the telescope was rather than using a single mirror, was to use a segmented strategy. So this has become the way that large telescopes are built today. It's the basis for the future TMT and the European Extremely Large Telescope. But at the time, it was really controversial. So the telescope mirror is made of 36 hexagonal segments, each of which is roughly 1.8 meters in diameter. So you have to align these segments to a fraction of the wavelength that you want to observe at. So initially, this was the first experiment that demanded that the telescope was lined up well enough, the mirror was lined up well enough to get to the diffraction limit, the theoretical angular resolution of the telescope. All right, so our strategy in the early days was very different than what we use today. So there was a first decade of a fairly simple approach to getting to the diffraction limit. Okay, so getting to the diffraction limit is hard for ground-based telescopes because of the atmosphere. It's great for us. It allows us to survive here on Earth, but it is a total headache for studying the universe. This gives you a little bit of a sense of the problem. This is actually some of the first data that we took on the center of the galaxy. What we eventually learned is that the black hole is exactly where this cursor is. We knew where to point, or we suspected we knew where to point, because there's an unusual radio source where the density distribution of stars peaks. Its name is Sagittarius star. It's an awful name for this object. It's a radio source where the people who discovered it in the 70s were trying to be clever. They were referring to nuclear physics, where asterisk means excited state. So it's really Sagittarius, not a star, because they were referring to the fact that it didn't look like a star. So this is the emissive source associated with the black hole. But it's a very wimpy source. It's like a very, 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 very faint active galactic nuclei source. But it could be easily explained by many other stellar accreting objects. Okay, so what we're seeing here are images that are 1/10 of a second. And what you can see is the distorting effects of the Earth's atmosphere. So if there were no atmosphere, each of these 5 bright stars would be the size of the smallest structures that are dancing around, and they would be rock solid still. So this is the problem of the atmosphere. And in the early days, we did a technique that's called speckle imaging. And speckle imaging works on the principle of just analyzing each frame as a set of interference patterns, so that you can deconvolve what the atmosphere is doing to you compared to what the underlying object is. So it's hardware simple. In other words, the number of modifications that we had to make to the existing instruments at Keck were pretty minor. They were just to change the plate scale, or the pixel scale rather, and to allow the electronics to figure out how to get the electronics to read out much faster than the instrument was originally designed to do, without making the read noise blow up. So it's hardware simple and software complex. So all the work was done in in software. Where we've gone, and that works out pretty well. And where we've gone is today is a technique called adaptive optics. I've actually left out the slides that show how this technique works, but let me just say that it's a system in which we introduce mirrors that can take on the conjugate shape to the wavefront error that's introduced by the atmosphere. So the simplistic way I like to explain this is you can think about the atmosphere basically being like a circus funhouse mirror, which distorts your images, and you want your deformable mirror in your adaptive optics system to take on the exact opposite shape so that your wavefront is once again flat. And this works amazingly well. And it's useful, again, to recognize what enabled these technological advancements. Adaptive optics was being developed within astronomy and astrophysics. But in fact, there are other communities that care a lot about looking through the atmosphere, including the military. And of course, the military has far more money than the astronomy and astrophysics community does. So in the mid 90s, it was declassified. And so in our field, there was a huge step forward in terms of just understanding. I mean, then the job became just understanding how to design these systems for astronomical uses. So Keck had one of the first scientifically productive adaptive optics systems on a large telescope. And here you see an animation that just basically shows the difference between a long exposure and a cleaned up picture. The 5 bright stars that we were looking at before are shown here. And then, of course, the stars of interest that we want to watch or we want to measure how they move are here. So again, this demonstrates that the techniques do work. You do see stars. And of course, I should have mentioned that the other feedback that we got in the beginning was concerned that you just wouldn't see stars at the location that were necessary, and that even if we did, that you couldn't actually see them move. So while we're going to focus a lot in this region in the coming slides, and in fact, what I'm now going to show you is just a fourth of the real estate in here. So you can see what's happened. I want to emphasize that we actually track a much larger region than is even shown here today. And we track thousands of stars. And it's important that we track those stars. In the beginning, for velocity dispersion work, you have to track all the stars to understand really what the mass is. And as you get into the orbit game, you need to track all those stars because you need to get into a constant astrometric reference frame. In other words, you need to position all your images so that they're all in the same coordinate system. And that turns out to be one of the hardest parts of this experiment in terms of where we're going today. So this is where, this is the central region, and it shows how the stars have moved over the last 25 years. You probably can find my favorite star in the galaxy or in the universe. Its name is SO2. It's the most powerful probe at the central potential because it has complete orbital phase coverage, both astrometrically, in other words, with images, so you can get the positions. And when stars are measured positionally or with images, they're trailed by a dashed line. Some stars pop up in the middle. It's not because they're getting brighter, but because our technology is getting better. So adaptive optics allows us to see much deeper than we could with the first decade of measurements and much more accurately. And then the other part of this animation that is important is that once adaptive optics comes online, you can actually measure not just images. You improve your positional accuracy by a factor of 10 and your sensitivity by roughly a factor of 10. But you also, for the first time, can take pictures at different wavelengths, and you can get spectra of these stars. And that's incredibly astrophysically rich once you introduce spectroscopy to this work along many, many dimensions. But for just understanding the central potential, that gives you the motion along your line of sight. Okay, so stars are trailed by a solid line once you can get to, once you obtain the spectra or the radial velocities the velocity along the line of sight for that particular star. So there's actually some evolution in just the instrumentation behind the adaptive optics that expands our ability to get spectra. Yeah, we'll just leave it there. Okay, so SO2, what does SO2 do for us? At the outset of this experiment, we knew that there was 4 million times the mass of the sun inside a very large region. This actually came from work done in the late 80s by Charlie Towns's group, where they were measuring the velocities through spectroscopy of gas. And the region that they could confine that mass to was really large. So it was so much larger than the region that you would need to demonstrate that there was a black hole, that if you, looking at their paper, the suggestion that this might be a black hole is not in the title, it's not in the abstract, it's a 1-paragraph suggestion in the discussion section. And that's simply because this radius that the mass was confined to was very large. And there were 2 other arguments that were made at about this time. One is that if you measure the velocity or the motion, the dynamics of the gas can be moved around by a lot of other things. So people were pointing out that there's a lot of massive stars in this region. These massive stars have winds. So the winds can affect the motion of the gas. So that was concern number 1. And then concern number 2 was that some of these bright stars, all these bright stars that you see, I'll just remind you that this is an adaptive optics picture, so just blur this by about a factor of 10, and you'd get what was known at the time. But these were recognized to be young stars, and as I'll get to, young stars are hard to form in the vicinity of a black hole. So in fact, people use the presence of these young stars at large radii to say, well, you couldn't possibly have a black hole because the tidal forces are so great that you would prevent or you would suppress star formation if this was indeed a black hole. Okay, so that was the framework going in. And what these orbits have done for us is to show that there is still 4 million times the mass of the sun inferred by those orbits, but it's confined to a volume that's a factor of 10 million times smaller. So since many of the arguments are around this, the case for a black hole is based on density, what this has done is to enhance the evidence for the existence of supermassive black holes by a factor of 10 million, moving it from a possibility really to a certainty. So the scale, just to give you a sense of scale, that these orbits have confined the mass to corresponds to the size of our solar system. Let me also point out that since this has gone in progression of going through velocity dispersions to orbits, the velocity dispersion gets you the first factor of 1,000, and then the orbits go the last factor of 10,000 to bring you the full factor of 10 million enhancement in the evidence. All right, so that's really what's being recognized with the Nobel Prize, which is the strength of the evidence for the existence of a supermassive black hole, which is now we now have the strongest case for the existence of a supermassive black hole at the center of our own galaxy, which is rather ironic because it's actually the active galactic nuclei that introduced the concept in the first place. Today, our scientific interest is no longer focused on the presence or the demonstration of the existence of the supermassive black hole, but has really moved in other directions. And the advances in our technology have really enabled a richness in the kind of science pursuits that we're engaged in. And there are many, many different offshoots based on the data sets that we collect that are primarily driven by getting the most precise measurements of the central potential through dynamical motions. So let me give you a sense of some of the problems that we're pursuing today. And there are 2 primary branches, as I started off with, sort of the physics piece, like tests of gravity, and then the astrophysical piece. So let me start with the astrophysical piece. the astrophysical piece, I have to say, has been, actually both of them have been incredibly fun. And they're fun because while we set off to, we define the experiment based on a clear question, there's actually more questions than answers that have come out of this work. So almost every prediction that one could make for what we should see around the central supermassive black hole based on our understanding of black hole host galaxy interactions has been inconsistent with the observations. So, I joke, you could say job security, or you could say kid in a candy shop, which is really what it feels like. There's just so many interesting problems. Let me just give you a few examples, 3 in particular, that this animation is designed to address. So in this animation, we color code the kinds of stars that we're tracking. So with adaptive optics, for the first time, we can understand these stars not just as the canonical test particle in a gravitational field, but we can astrophysically understand what kind of stars these are. And as I've already alluded to, people, you don't expect young stars in this region because of the strong tidal forces. And not only are there young stars out at distances where we could measure before these high resolution imaging techniques came along, but now with adaptive optics, you can see that the dominant population in this field are actually young stars. Oh, I should mention, so this makes sense, that the blue-green stars are the young stars. So they're the most common kind of star that we see, the ones that we say shouldn't be there if there's a black hole. So now we're sure there's a black hole, and there are these young stars. And I like to call this problem the paradox of youth. The problem is quite pronounced. So the way one can think about the problem is, if you think about the gas densities that are necessary to overcome the tidal forces of the black hole, in the center of this image, in terms of the distances there, the densities would have to be a factor of 10 to the 11th times higher than what is seen there today. So it's not just a little inconsistency, it's an enormous inconsistency. And this has driven a lot of theoretical work in terms of how can you get what appears to be young stars in this inhospitable region. And the classes of solutions that have come up are really threefold. One is perhaps this environment creates stars that look like young stars, but aren't. They're old. They formed someplace else. They migrated in. Maybe they're dark matter infused stars so that they look, they have different characteristics, or they alter their characteristics. So that was one class of solutions. Another class was maybe these things are formed elsewhere and migrate in very quickly. So they would have to migrate in on a timescale of 1 million years. That's very rapid for dynamical friction. So basically just interactions with the background. So that's an idea, but that would leave a trail of stars. And these stars really do look young. They don't look, there's nothing about them, as we've been able to study them in more and more detail with more advanced instrumentation. Spectroscopically, they look like just a typical young star. And as you see in this animation, it's like right at this point, what has emerged over time, because the orbits get to be longer periods as you go further and further out. So you have to be patient, and you have to develop your understanding of the central potential to get the orbits at larger radii. But as these are emerging, you see that many of these young stars share a plane, a common, or basically have a common angular momentum for their orbital angular momentum. And that's suggestive that they did form in a pre-existing accretion disk, which has a lot of interesting implications. So if the densities were much higher in the past, just a few million years ago, that suggests that our galaxy probably was much more like an active galactic nuclei in its relatively recent past. And there's definitely observations at higher energies that suggest that indeed could be true. So that's our current thinking about the young stars. The old stars, the orange stars in here, the old stars should be, the prediction is that there should be tons of them. And in fact, we use that prediction that the density of old stars should be enhanced near the black hole. That's often used to find black holes at in more distant galaxies, where you look for the enhancement of stars or at the center. And yet we don't see them. Where are they? There's a dearth of old stars. And then one of my favorites, I have to say today, are the pink stars, the magenta stars. These are things that we didn't even think to predict. These are the first spatially resolved, tidally interacting objects at the center of the galaxy. And you see their geometry evolve through our observations. I should say, these really required adaptive optics. You don't see them at 2 microns. They're so red, they're so cool that you only see them at longer wavelengths. It's super easy to see them in a 3 or 5 micron image. And then we also see them spectroscopically through emission line observation. So you see them far away, and as they come towards the black hole, they stretch out, they elongate, they pass by the black hole, and they become compact. So this has been an interesting study. The first example of it, of this class of stars, was called G2. And my current, and again, there's been a lot of different thinking about what these objects could be, ranging from gas clouds, the original suggestion, to what intrigues me today, for reasons that I'm happy to get into later, is the idea that these were originally binary stars that the black hole drove to merge through 3-body interactions known as the Kozai-Lidov effect. And if you start to think about the role of black holes in driving binary star mergers, this actually potentially provides some useful insights into the gravitational wave sources, which are producing stellar mass black holes that are much larger than we expect, and that are occurring more frequently than we expect. So understanding the role of central black holes in driving mergers might provide some interesting insight. So I'm not suggesting that these are stellar mass black holes. These are probably 2 typical main sequence stars, so stars like our sun, that were driven to merge. And when they merge, they become really bloated, and it's easy to tear off the outer shell of these stars. So these are tremendously fun, and have also driven us to really look for and understand the binary star population at the center of the galaxy, which is yet another angle. Okay, so I'm going to leave it there. There's actually a lot more that you could say astrophysically, because I really want to end this talk with a few comments about where we are on the sort of fundamental physics probe. Once you have complete orbits, you actually can start to you enter the regime of being able to do some of the first direct tests of how gravity works near a supermassive black hole. So I want to emphasize, you need a complete orbit because you need to know the geometry of the star's trajectory, the shape, where the star is in space-time. Okay, so that short period star that I emphasized before, SO2, its orbital period is 16 years. So this is an experiment that really requires patience, because you got to wait 16 years. And then the next time it goes through an important turning point, which is either the closest approach or furthest approach, you're in business. So for many, many years, that was, we were focused on 2018 because that was that moment where you had a complete orbit and you get to the first closest approach. And now we're headed towards the first furthest approach. And I'll share why that's important. So the first closest approach allows you to really get at tests of the relativistic redshift. Okay, so what you're looking at there is you're looking at the test of looking at how the photon is affected, how it loses energy as it climbs out of the gravitational potential well. Okay, so it's an extra term on the Doppler shift. And then so I'll show you the results of this. And then you're looking for the precession of the periapse, which is looking at how the object itself moves through space-time. So the idea that it's not going to come, the orbit will not come back to the exact same place, but will go in a prograde sense if you're only affected by gravity. Okay, so 2018 was a really fun year for us. It turns out there were 3 important measurements within the course of 6 months. So we used to say we were 2018 or bust. But I really want to emphasize, okay, so the prediction is that the extra effective shift, wavelength shift over the Newtonian piece. So you can see that there's this huge change going from 4,000 to minus 2,000 kilometers per second as it goes through closest approach. And there's this extra 200 kilometer per second piece that we're looking for. Okay, so this plot is the measurements, and these are the measurements relative to the best fit Newtonian component. Okay, so you're looking for this extra 200 kilometers per second. The dashed line here is the expected from GR. If it were purely Newtonian, well, you're differencing it from Newtonian, so it'd be flat. So you definitely see this 200 kilometers per second. I want to warn you, though, to think about this plot carefully because it's differential. and the biggest source of uncertainty is the geometry of the orbit. Okay, so everything is well behaved, and this measurement will just get better as you understand the geometry of the orbit better. Okay, so today, first probe, Einstein gets a check. Okay, what excites me more, is where we are today. Okay, so this is ready to, at least I'm ready to talk about this, but I'm also ready to tell you why we're not publishing it yet. In other words, why you should be skeptical. So the next part is the precession of the orbit. So again, this theory is really exaggerated. So it's the precession, prograde precession. So the orbit should go in the direction of the orbit. The precession should go in the direction of the orbit. But what we actually see, and this is very preliminary, is the orbit going in the opposite direction at twice the rate. Okay, so like the other, when things don't work as predicted, that's when things get interesting. Okay, so why? Let me just take two perspectives. One is you've got the physics right. Okay, so what gives you the retrograde orbit? What can give you the retrograde orbit is extended mass around the black hole. And SO2 is on quite an eccentric orbit. It's higher, it's slightly higher than 0.8. So what you're really seeing is the difference between the mass at closest approach and the mass at furthest approach. And how we model this is the mass that is within the furthest approach, which is 0.01 parsecs. And it's slightly under 20,000 times the mass of the sun. Okay, so that's an interesting number. And it's further interesting because remember I said that the cusp is missing in the old stars? If you think about how much mass should be in the cusp, it's about this value. So it's not crazy physically, but here's why you have to be concerned. Unlike the spectroscopy piece, the gravitational redshift, which is really mostly a spectroscopic measurement, this is mostly in the imaging space, the precession. And what's really hard, unlike the spectroscopy, which is really easy to put relatively easy and relatively well established how you do this, how you get everything in the same coordinate system. You just use you use quantum mechanics. Here, you have to use you have to get into a constant astrometric reference frame. Anybody who does astrometry, positional work will tell you this is really hard. And at the Galactic Center, it's even harder because you're in all your reference stars are in the same central potential that you're trying to measure. So you have to be very careful, and it's very easy to go wrong. Okay, so this is why you should be suspicious. I could say a lot more, but this is what keeps me up at night these days. But it's worth working harder on because it's a really interesting thing to get into the probes of precession, either as a test of GR or as the discovery of dark matter at the center of the galaxy. Okay, I'm not going to go into these next slides except to say we're working a lot on new technologies, improving our adaptive optics system, which of course is important for KEK and the future 30-meter telescope or the European Extremely Large Telescope. Pick your large telescope. All of this is important. And today we only see the tip of the iceberg in terms of the stars that we see. So all of this is going to open up so much more. I mean, we're really only seeing the brightest stars. And the analogy I like to make is it would be like trying to understand the economy if we could only see the biggest transactions. So it might be that we see all these mysteries simply because we can't see the bulk of the population. Most stars are faint, not bright. So we're missing all those small transactions or those small stars. Okay, so if nothing else, I hope I've convinced you that we have extremely strong evidence for the existence of a supermassive black hole at the center of the galaxy. And through the development of technology, we actually have more questions than answers. So there's lots more that remains to be done. Thanks for your attention.
Thank you very much. This was a beautiful and inspiring talk. So are there any questions? Please raise your hand.
There's a couple of questions already.
So where do you see them?
On participant list.
Sorry, yeah. So Kenny Vetter.
Hi, great, thank you very much. This was a fantastic talk, thank you so much. I'm curious about the adaptive optics. So let's say that you are able to effectively reduce all of the atmospheric noise that you have. Are you then diffraction limited, or is there another noise piece that becomes dominant, say acoustic noise or vibrational noise or just shot noise or your dark current? What for your setup, what becomes the dominant noise contribution?
Well, right now, we're still limited by the atmosphere. So behind me, you see the two kecks, and you see one laser coming out of each. It's just actually, so it's two adaptive optic systems. They're running independently. But let me just emphasize that with one laser, where you're creating an artificial spot, actually what you're really doing is there's a thin layer of sodium atoms up at 90 kilometers, thanks to meteorites coming down to the Earth. And the structure of the atmosphere just happens to trap sodium atoms up at 90 kilometers in a very thin layer at 4 kilometers. So you take a laser, you stimulate those sodium atoms to shine, and you have an artificial star. 90 kilometers is really close compared to your stars. So if you think about the geometry of this, you have the artificial starlight coming down to your telescope in a cone, whereas your starlight from the center of the galaxy is coming through a cylinder. So this is called the cone effect, because you're only probing this cone, and the larger your telescope is, the more pronounced this cone effect is. So at the center of the galaxy today, with one laser, you only get correct 30% of the atmospheric problem. So you put 30% in a diffraction limited core, and then you have this halo that remains. That's sort of the original seeing that this diffraction limited core sits on top of. So the first thing is to do that multiple lasers. So you're basically doing what's called laser tomography, so like a CAT scan on the atmosphere. So through those different probes, you can actually get rid of the cone effect. So that helps you at Keck, but it even helps you even more for the next generation of telescopes. So for the next generation of telescopes, if you only had a single laser, you would only correct about 3% you'd have 3% of your energy in a diffraction limited core. That's kind of like speckle era performance, which is pretty lousy. So you really need that next set. And there are a whole bunch of different pieces that you have to think through in terms of what might limit you. So it's not only your mapping of the atmosphere, but it's in your deformable mirror that you're moving around, how many segments are in the deformable mirror. So today, if we go to this multiple laser system, what will then limit us is the fact that the segment size in our deformable mirror is too large. If you can overcome all of these problems, well, I mean, the adaptive optic systems are so complicated that you hit your performance is limited. You always hit you try to reduce the tallest tent pole, So let's see, we've got the lasers, then we've got the deformable mirror. And then another piece that you have to pay a lot of attention to is the read noise of not your science camera, but the read noise of the detector that's looking at your either your artificial star or what I haven't talked about is you need a natural star to give you the overall tilt. So there's two camera systems supporting your adaptive optic system. So then you have to worry about that, the read noise of that, because you have to read out so quickly. You're really read noise limited there. So it's really exciting that a lot of people are developing next generation adaptive optic systems, because each system thinks about a different component. So they're really they're complex. There's lots of room for improvement.
Yeah, I had no idea. That's fascinating. Thank you so much.
There is another question, Kewal Chetri.
Am I audible?
Yeah.
Thank you, ma'am. So I have one fundamental question sticking on my mind. So in a thought experiment, we can make out that there will be distortion in the space-time fabric when we imagine a mass. So that means if we imagine that there is nothing in this universe, there would still be an unbent space-time fabric. So I want to know that what would be the origin of this unbent space-time fabric?
I don't know. I'm not sure I understand. I mean, are you asking me what, are you asking me the source of the dark matter that we might be seeing?
Ma'am, actually, I don't know about the dark matter, but at least for now. So.
Okay. So maybe we pass to the next question, Alvaro.
Hi, thank you for the talk. Coming back to dark matter, the day you begin to be convinced that you have seen something like dark matter, how are you going to decide it's something interesting and not lots of gas or Jupiters or something like that?
That's a great question. You know, how do you disentangle the various baryonic compared to non-baryonic sources of dark matter? And I think one possibility is by the time you get to the 30-meter telescope, you can start to look for the discrete events that I guess from your perspective would be the non-interesting version. But it is a hard problem. So, you know, we have to solve the first problem of believing it. And then the second problem of what is it? So I hope we get that opportunity to think that through.
Do these standard models of dark matter in the center of the galaxy agree more or less with the amount that you think might be there?
Well, you know, the cross sections have come down. So at the beginning, the amount of dark matter from particles versus say, you know, stellar remnants were comparable. But today, the predictions are that the particle cross sections are so low that they're not, that you would expect it to be the non-interesting one.
I see. So thanks very much. I'm not going to continue because you probably have things even more important than talking to us.
It's been a pleasure to talk to this audience.
Yeah, so it has been our pleasure to listen to you. It was really fantastic. So thank you very much for your time. And this is
just a minute. On behalf of the network and on the workshop, I want to thank you for your kindness of being here. I will get in contact with you for the diffusion of the video, but offline. And thank you very, very much. This was great, really great. And we hope it's not the last time you are here with us. So thank you so much.
Thanks for the invitation.
Okay, bye.
Thank you.
Have a nice day.
So now, Belen,
Yeah. So guys, we are approaching the end. So just wait a minute, because there is somebody we have to liberate here, which is, let me just share the screen. Well, no, before sharing, what I want to give you is a big thank you to all the participants, to all the speakers those who have pushed up the physics. And I think even being an organizer, I learned a lot. I think there has been great, I have learned a lot, and also for the questions and everything. So I want to thank everybody very much for their participation. A special thanks to the quite a few people from from time zones disconnected from us, from the West Coast to Japan even. So that's an effort. So thank you very much for being there. I know it's more difficult with Zoom. And what, as I was saying, I just want to, of course, in particular, share, let's see where it is. Here, you see this? So you remember at the beginning when I explained the origin of the bear in the coat of arms of Madrid and the madroño, or in English, arbutus, in Latin arbutus, arbutus udeno, the guy was eating the berries of this tree. So he came down, or she, maybe a she, and has started watching our workshop, right? As forced by the drawing of Salvador Rosauro. So there it is. This poor female or male has been there all the time, so is close by.
It's Ursa Mayer, it's female, clearly.
It's female, okay, yes, it's female, clearly, okay. So it's Ursa Mayer, you are right. Ursa Minor, no, we don't know, is the.
Well, but they are both Ursas. So
it's both Ursas, so yes, you are right. So it's a female, very good, whatever, I'm happy with both. And okay, so so I should thank, there she is still watching. And I want to thank the organizers. Here you see the scientific organizer committee, international and local, all mixed, and the juniors have been fantastic. All these things that work all the time is due to them, the timing, the everything. And of course, our management team, Rebecca and Chabeli, who are sustaining both the network and this workshop. And so on behalf of everybody, I want to give a big thanks to them. Okay, maybe the names are better. You can read the names there. This time I don't tell them one by one, right? So I leave them a moment, and I pass the stage for the final comments to the coordinator, Silvia Pascoli. So thank you very much to everybody for the help, for all the work, and for the great physics. So I stop sharing the screen. And Silvia, please, are you there, Silvia?
Yes, I cannot share yet. Maybe you can share the slides for me, or?
You want me to share? Okay.
Yes, I cannot share my screen.
Okay, so
I'm host. Okay, then I can share. There we are.
Okay, there.
So, but this is just to kind of close the meeting. I think it has been a real pleasure, even if online. Still, we listened to some great physics, and we had the opportunity to discuss together. Belen thanked everybody else, so I really want to thank Belen for the organization of the meeting in difficult circumstances. But I think Belen and all the team in Madrid did a fantastic job. Of course, I want to thank the participants, as Belen said, coming from all over the world, the speakers. It was really a privilege to hear Andrea speaking, and all the other senior and junior speakers as well. And I want just to give you the appointment to next year, the Invisible 2022 events, the school first, followed by the workshop. They will be organized by the CNRS node, and we expect you there, hopefully in person. Let's keep fingers crossed that we will be able to do that. Otherwise, we find a different solution. This is the details. We will be at the Auditorium Perleman in Paris, and we're already planning our nice social activities. If we can, we'll go to the Musée d'Orsay, and I've been once for a conference dinner. It is really fantastic with access to the permanent collection, and a really, really great experience. So
yeah,
yes.
the chair, we forgot to put there, chair next year
Yes,
is
so
Asma.
Asma Abada and Damir Bečirović will be the main organizers, and of course they will be supported by the other people at CNRS and the ESRs that are there. And with this, I think I remembered to thank everybody, and thanks a lot for being here till the very end of the meeting.
Okay. Have a nice weekend. Bye-bye.
Thank you.
Thanks.
Bye-bye.
Bye.
Bye-bye.
Bye.